All right, we're looking at Chapter 3, Section 2, Complex Numbers. Now, there's lots of videos about complex numbers, and they will explain it a whole lot better than I will. So I'm just going to show you how to complete the problems. If you want to know more about what complex numbers are, how they came about, that kind of thing, I would just go on YouTube and search up complex numbers, and there's surely to be much better videos than how I can explain it. Right here it says not all quadratic equations have a real number solution. Right, that would be like in my last video, I talked about maybe you'd say no solution or zero solution. For example, we look at x squared equals -3. Right, there's no way that two of the exact same numbers can multiply together to give you -3. And the idea there, the reason for that is that if you have a positive number times a positive number, well, that gives you a positive number. And if you have a negative number times a negative number, well, that still gives you a positive number. There's no way to have two of the exact same number multiply together to give you a negative, right? There's no way that two numbers can multiply to give you a negative, right? There's just no way for that to happen. Now, people a long time ago saw that, and they came up with this other, this other way to talk about these kind of problems, and they say, well, we're going to have I as an imaginary number. And they say that I is the square root of -1, and then more importantly, I squared is just a plain old -1. Right? And again, that doesn't make sense, and that should be weird. It should be uncomfortable. There are no two numbers that multiply to beat a negative. Right? Excuse me. There's no two numbers that multiplied that are the same number that multiply to be a negative. So right here in example 7, let's dive into that. We want to get x by himself. We're going to say x equals, we take a square root, plus or minus the square root of -3. Now again, that negative, that just doesn't work, right? That's not allowed. Now we're going to have this I to be a symbol to say, well, maybe it's not allowed, but we're going to talk about it anyway. And we're going to talk about this imaginary unit. So what we're going to do is we're going to break apart the -3. We're going to say plus or minus root -1 times 3. Right, just breaking it up. And then I can break up over that product, and I can say, well, square root of -1 times the square root of 3. And then the square root of -1, by definition, is I, right? That's the definition that we had right up there. So I'm going to say plus or minus I square root of 3. And that is going to be our answer. Now what this means for us is that we have imaginary solutions. They're kind of like fake solutions, but not really, but we might think of them as fake, especially in the beginning. No longer can we say no solution whenever we get something like there's a -4 under a root. We can't say no solution anymore. We can say no real solution still, but there are complex solutions. And this right here would be a complex or an imaginary solution. Okay, so it's just a new way to talk about these things. Example 8, it says to find the square root of -108. Well, for starters, the negative is going to turn into an I, and you have I root 108. Right, so I kind of skipped some steps that we had up here. I took the negative, I broke them out to a -1, then I said, well, he's the square root of -1, whereas down here I just said, hey, there's a negative, so he's going to turn into an I. You are welcome to just jump straight to this step right there. Now that we have this, the I is just going to hang around while we take the 108 and break them apart. So the 108, we look for factors of 108, because we're going to try to pull something out. 108, I'm going to divide by 2, and I get 54. I'll divide by 2 again, and I get 27. 27 is 3 times 9, and 9 is 3 times 3. Now, so I have prime factorized this. I've broken them down until we got primes. The 2 and the 3, those are prime numbers. Now, because this is a square root, I'm going to circle pairs of 2. So there's a pair of 2, there's a pair of 3s, and there's a single 3. Now, the pairs get to come outside. So I'm going to have a 2 outside, a 3 outside, and then I have this leftover 3. He's going to go inside. The I is just hanging around in the problem. We treat him like a variable. And then we have our radical, and then we have our 3 left underneath. So this set of 2 became this 2 on the outside. This set of 3's became a 3 on the outside. And then the singleton 3, he stayed inside. Multiplying back together to make it pretty, 6i root 3. And that is our answer. One thing to make note of is that right here we don't have a plus or a minus, right? Up here we had the plus or minus in our last problem. That is because we... All right, sorry about that. In example 7, we had the plus or minus, right? And that's because up here, up in our first step, we made the square root, right? It started off without a square root. It was just an x squared. But then we took the square root and we put in the plus or minus. Down here in example 8, the square root was already written, so we don't have to have a plus or minus. All right, down here, this blurb here just talks about how when we have a complex number, there's a real part, which is just a plain old number, and then an imaginary part, which has an I. So we're going to have a plus bi. We treat the I like he's a variable, and we can combine like terms. The big thing that's a little bit different than what we've done before is, say we have, think about y equals maybe mx plus b. Right? Slope-intercept form. We've all used that before. We put the x in the front spot. Whereas with the imaginary, we put the letter, the I, at the very end. So you can read this blurb if you'd like to. I'm going to go on to example 9. Right here we have two complex numbers. The complex numbers have a real part. So this first complex number, the real part is 7. The imaginary part is 4. Well, I guess it's 4i. You could say 4i. The other one we have 5 and then negative 2i. There's a plus in between them. We drop the parentheses. I drop the parentheses, and then you can just combine like terms. The 5 and the 7 can go together to be a 12. The 4i minus 2i is going to be 2i. And that's it. Let me draw my I a little bit better there. There we go. That's all we got to do. Number 10 steps it up a notch because we got this negative that we got to distribute. So I'm going to say 8 minus 3i minus 4 minus 5i, right? The negative distributed to both the 4 and to the 5i. Now the problem is just like example 9, and we just combine like terms. So we got 4 minus 8i. That is example 10. Let's scroll down. Example 11. Now here we're going to have to distribute. When we distribute into the first part, we get 20i. And then when we distribute to the second part, we get plus 2i squared. Now, what's unfortunate about this problem is that we're not allowed to end with an I squared. We can have plain old numbers, or we can have plain old i's. We can't have an I squared, or like an I cubed, or an I to the fourth. And we're going to have to go back to our definitions to figure out what is I squared. I is the square root of negative 1, and then I squared is just a plain old negative 1. So right here, I can plug in negative 1. So it's going to be 20i plus 2 times negative 1. This gives me negative 2 plus 20i. And that's going to be my answer for this one. So there's number 11. Let's look down at number 12. This time we get to distribute again. The 3 times 4 gives me 12. 3 times negative 2i gives me negative 6i. I times 4 is 4i. And then I times negative 2i gives me negative 2i squared. Now again, that I squared, we're going to plug in a negative 1 for that. So I'm not going to change anything else. I'm going to say 12 minus 6i plus 4i. And this is going to be negative 2 times negative 1. The 12 and the negative 2 times negative 1 is going to be a 14, right? Because the double negatives make that guy positive. And then we're going to have minus negative 6i and 4i gives me negative 2i. There we go. That's example 12. Down here, what's a conjugate and what's a complex conjugate? Well, a conjugate, we oftentimes think about those in pair. And this should be reviewed from Algebra 1, but we might not remember. If we think about something like 3x plus 4, that's a binomial, right? Binomial because there's two different terms there. His conjugate is going to be 3x minus 4. The only thing that changes is the symbol between them. Now, we're going to go ahead and multiply this out. 3x and 3x is 9x squared. 3x times negative 4 is a negative 12x. 4 times 3x is positive 12x. And then 4 times negative 4 is a negative 16. Now, right here, negative 12x and positive 12x, those are opposites. They cancel, and we're left with 9x squared minus 16. Conjugates, they make things cancel. So for real conjugates, right, these would be like real numbers here, you distribute them in the middle terms cancel. A complex conjugate, we're going to have even more canceling. So what if I had 3i plus 4? His complex conjugate would be 3i minus 4. Now normally we'd put the i's in the last spot, but I'm just wanting it to look a whole lot like our real number up here, so I have them written kind of backwards. Whenever I distribute, I'm going to get 9i squared minus 12i plus 12i, and then minus 16. Like in our last problem, the negative 12i and the positive 12i, those cancel, and we're left with 9i squared minus 16. But wait, there's more. The I squared is negative 1, so we have to do even more, right? We have to say, well, 9 times negative 1 minus 16. Uh-oh. Oh, there it goes. Negative 9 minus 16, and what is that going to be? Negative 25. So let's look back at what we had here. We had a real set of conjugates. Those canceled out the linear terms, and we were left with a quadratic term and a constant term. With the imaginaries, we had an imaginary part and a real part. They canceled out the plain old imaginaries. Then we had an imaginary squared and a constant. Imaginary squared turns into a constant. So we had the constant negative 9 and the constant negative 16 to give us the constant, the real, negative 25. So that's really neat. When you have complex conjugates that multiply together, you get a plain old real number in the very end. Now, somewhere on the homework, I'm thinking we're going to need that. So hopefully that makes sense. If not, there's lots and lots of videos on conjugates. Go ahead and Google what a conjugate is, or see some people working with conjugates and multiplying. All right, I believe that's the end. Yep, that's the end of section 2. Big idea. Let me find where it was written down. I squared is a negative 1. If you don't remember anything else, that's the thing to remember. All right, that's all.